So this video is about limits to infinity, and we're going to be looking at polynomials and its big brother, the rational expression, which has a polynomial for the numerator and a polynomial for the denominator. So let's look at polynomials. So when you go to infinity, the leading term is the one that decides what is actually going to happen to this function. And here's why. If we take 1,000,000 and square it, like this, then we would get this, without the parenthesis. So it's just, so you have 6 zeros, you would get 6 and then another 6 zeros. Now if we do the same thing to cubed, we would get this, which would give us this. And so you could see what we ended up getting is something that is now 1,000,000 times larger. So it's this times 1,000,000. And if you keep doing that, so if we did 1,000,000,000 and 1,000,000,000, then this would be 1,000,000,000 times larger, 1,000,000,000,000 and 1,000,000,000, then this would be 1,000,000,000,000 times larger. So this one is growing a lot quicker than this one. So who decides what happens to this polynomial? It's our first term. It's our leading term with the biggest degree. So when we look at this, all you have to think about when we're doing our limit is the first term. This is a polynomial going to negative infinity. So if you were to plug a negative infinity into x cubed, which we're not really doing, it would become negative infinity. And you can check this very quickly with a calculator. So if we plug our polynomial in, and then to do that, you go to your table, and we start this at a really negative number, and then we want our change in table to go the same way. So we're going to do more negative that way. So this way we're starting at a really negative number, a really large negative number, and then we're increasing that negative number. And so it'll tell us what happens when we plug in our polynomial. And you can see you get -1e to the 24, which is a massive number. And if we keep scrolling down, it's just going to keep getting bigger and bigger and bigger. Well, in this case, smaller and smaller, more negative and more negative. And so it's negative infinity. That's what we're getting. So the easiest way is to just look at our end behavior. And if you remember, this was negative x to the odd. This was x to the odd. This one is x to the even, and this one is x to the, negative x to the even. So if your leading term is negative x to the odd, we know it's going to have this end behavior, meaning going to negative infinity, we are going to be going to positive infinity. And going to positive infinity, our function would go to negative infinity. So you can tell which direction it's going as you move across. So that's how you want to look at each of these. So if we have the limit as x approaches infinity of negative x to the cubed plus 4x minus 2, all you have to do is focus on the first term. So this is going to equal the limit as x approaches infinity of negative x cubed. And then what does our negative x cubed look like? Well, negative x cubed does this. It goes up, and then it goes down for its end behavior. And we are looking for the positive, so this one. And which direction is it going? It's going down, meaning our answer would be negative infinity. Okay, so that's how you want to look at polynomials. Just look at the end behavior for each of your functions. All right, let's try rationals now. So with rationals, we're going to be using this limit law. So the limit as n approaches plus or minus infinity of 1 over n to the r is equal to 0 as long as r is greater than 0. It's very important that r is greater than 0. Because if r was not greater than 0, then what we would end up with is 1 over n, right? And if r is, say, less than 0, like -2, this would be n to the 2. So it turns into one of our polynomials up here, which means it's not going to 0. It's going to negative infinity or positive infinity, depending on what the polynomial says to do. So very important to make sure that your r is greater than 0. But if it is, we can apply this law. And this is just our, remember our rationals before? When we had a degree that's bigger on the bottom, this one goes to 0. So like this. And we end up with this. And so now if we test it, I already have it set for negative infinity. It doesn't matter if it's positive or negative. So when we check our table, you can see it's getting really small. It's going towards 0. So if I keep getting bigger and bigger, more and more towards infinity, you can just see it's getting smaller and smaller. Remember, negative 60 means the number of decimal places that we would have past this 1. So we'd have to move over 1 and then 59 more. So that's 59 zeros before we would hit 1. This is approaching 0. So that's what happens here. So we're going to be using this for every single one of these. We want to make these tiny little fractions. And if you can make these tiny little fractions, we can say that those go to 0. So I'm going to show you two different methods, the standard one and then a different one involving factoring. So what we want to do is rewrite limit as x approaches infinity. And then you take the denominator, the degree of the denominator. So in this case, it's an x. And you want to divide every single term by x. So what we're doing is multiplying the top and the bottom by 1 over x. Top and bottom by 1 over x. Now if you simplify this, we get 1 plus 3 over x, and then 1 minus 4 over x. And then we know now that the limit as n approaches infinity of 1 over n, in this case it would be the limit as x approaches infinity of 1 over x, is going to go. So the limit as x approaches infinity of 1 over x is going to equal 0. So we know this one goes to 0, and we know this one goes to 0, and it's okay to write that notation. And so we end up with now 1 plus 0 over 1 minus 0, which is just 1. So the limit of our function is 1, and we can check it in our calculator. So now I've already got it set, so let's just look at our table, and you can see it's 1. The calculator just zeroes out and says, you know what, it gives up and just says it's 1. And there you go. So now let's try another one. So our bottom degree here, the biggest one that we have, our leading term would have been negative x squared. So we're going to divide everything by x squared. So the limit as x approaches negative infinity of 2x over x squared plus 3 over x squared, and then 5 minus x squared over x squared, and then we cancel. So this becomes the limit, and make sure you are writing the limit each time. So this is 2 over x plus 3 over x squared, 5 minus 1. Oops, I forgot the x squared over here. Very important. There we go. Now everything looks good. All right, and then now we can use our rule. So the limit here again as x approaches infinity of 1 over x is equal to 0. So this would go to 0, this would go to 0, and this would go to 0. And now it just says x, right? And so we can just put a little r up there with r greater than 0, and that counts for all of them now. So we get the x squared, and the other x squared here. And so what do we end up with? Well, on the top, it's 0 plus 0, and on the bottom, it's 0 minus 1. And then this is 0 over negative 1, which is 0. And so there is your limit. And again, we check it in the calculator. So there it is. Plug it in our table. And you can see it's that 0 situation happening again. So we're getting smaller and smaller. We went from negative 29, so 28 decimal places, to 29 decimal places. And you can see it's getting smaller. We went from 7 to a 2, and then this is going to kick down to a 31. It's going to 0. And there you go. Now, what if they're already set up for you? Well, then you can just apply it. So we know the limit as x approaches infinity, in this case negative infinity. Probably should write negative infinity on that one up there as well. Of 1 over x to the r with r greater than 0 equals 0. So we know that one's going to 0 and that one's going to 0. So 3 is just 3 plus 0 plus 0. So the answer is 3. So if it's already set up for you, just plug it in. There's no reason to combine it into a rational function and then start splitting it up if it's already ready for you. So we have one more here, and if you've noticed, we've gone through each of the types that we have. So the degrees are the same. Remember, we just look at the coefficients. So looking at this, you should already know with your rational functions and your horizontal asymptotes how these, what they approach. So this one's approaching 1. This one's bigger on the bottom, so it's approaching 0. And then this one's bigger on the top. So we know this one's going to go off to infinity or negative infinity. It's our slant asymptote. So if we apply our rules from before, we can show that that is true. You can't just say, oh, it's negative infinity to infinity. You've got to show work. So if I put a little parenthesis, a little highlight there, we always pick the bottom. And so now that is what we're going to divide by. See, the reason we're picking the bottom to divide this by is we want to make sure that our bottom maintains a non-zero number. And so if you're always dividing by the biggest degree, you're going to end up with something that cancels nicely, giving us a nice whole number. So we pick the x squared so that when we continue negative infinity, we end up with -1, not 0. Even though this will turn into 0 at the end, we're still going to end up with a nice number on the bottom. So non-zero. So we know that this goes to 0, this goes to 0, and this goes to 0. Let me put my parentheses back around there. Make sure, by the way, if we start with negative infinity, that negative infinity travels through the entire problem. Okay. Now we end up with limited as x approaches negative infinity of x over -1, which would mean that this is the limit as x approaches negative infinity of negative x. There we go. It's that whole transfer there that got me a little stumped. So now it's -x. And so this is our polynomial. It's just our line, just like we knew with our slant asymptote what it would be. So this is a linear equation going down, which means we're going to be going towards negative infinity if we went that way, and positive infinity if we go the other direction. So which way are we going? We are going towards negative infinity. So we know that we are going this way towards negative infinity. So our answer will be infinity. But you can also just plug it in by thinking about it. So if we had negative, we plug in the negative infinity just like before, we end up with positive infinity. It's not really what we're doing is plugging it in, but it's kind of is because we're approaching infinity. It's going to go towards infinity with a negative, so we end up with positive infinity. Checking that in the calculator, I've already plugged it in. So there's our original rational function. I've got it set with both negative because we're going to negative infinity. I hit the table. And look at that. It's all positive, getting bigger. You can see how it's getting bigger to the 9, and then 1 e to the 10. And then it's going to go 1, 2, 3, 4, 5, 6 e to the 10, and then to 11, and so on. It's infinity. All right, now I did say I would show you an alternate method. So if you don't like dividing, you can always use factoring. So what we're going to do is, instead of dividing everything by x squared, we're going to factor it out. So it's just the same idea as we're trying to get that x squared out. So if we factor out the degree on the bottom, we would end up with x squared on top, and then x plus 2 over x plus 3 over x squared. And on the bottom, we would end up with x squared, and then we would get -1 minus 1 over x. So you can check this very quickly. If you factor out an x cubed, this one's missing 2 of them, right? Or sorry, we factor out an x squared. This one is missing 2 of them, or 1 of them. And this one doesn't have any x's, so it's missing 2 of them. And then we factor out the x squared here. This one was all x squared, so we take them all out. And this one only had 1x, so the difference would be an x. But you can check it just by multiplying back in. And you'll see that it cancels and gives us the original. And then now we can apply what we're doing. So again, we're always trying to get those leading terms by themselves. So that's 0, that's 0, that's 0. And so now these cancel. We end up with the limit as x approaches negative infinity. And then on the top, it's just x. And on the bottom, it's -1. So see, it's the same thing we got up there. So this will equal the limit as x approaches negative infinity of -x, which is positive infinity. So this would work for every single one of them. So if I do the top one again the same way, we do the limit as x approaches infinity of x plus 3 over x minus 4. Our denominator has again an x to it. So if we factor that out, we get the limit as x approaches infinity of x, and then that would be 1 plus 3 over x. and then x, and 1 minus 4 over x. And again, that goes to 0, that goes to 0. So we end up with those canceling. The limit as x approaches infinity of 1 over 1, right? And that's just 1. So we don't have to even write limit anymore. It's 1. And if you do the bottom one, the next one that is, we're going towards negative infinity. Then our 1 is on the bottom here. And so we get the limit as x approaches negative infinity. And again, we always take out the leading term, the biggest one for the denominator, that degree. So we're going to factor out x squared on the top and factor out x squared on the bottom. So this would be 5 over x squared minus x squared over x squared. And then this, so it already has 1, so I would factor out 1. I don't know what happened there. Factor out 1, and so I'd be left with 1 more. So this is 2 over x plus 3 over x squared. Cancel, cancel, goes to 0, goes to 0. Oops, wrong one. Undo. Goes to 0. And we would end up with on the top 0, and on the bottom cancels to make 1. So it would still be 0. So you need to find the preference that you like. I like dividing by the leading term on the denominator. It just, to me, is a lot simpler. But if you like the factoring method, you can try that as well. Thank you.